Welcome back to Math 1720, starting chapter 6 now. So we're going to be going through the inverse circular functions. Okay, we've done all this before using degrees. Now we're going to do most of it using radians. Okay, remember, essentially we're finding the angle given the ratio when we do these calculations. Alright, this one is a little bit of a lengthy lecture. We're going to go through the first two sections here. Alright, and before we move on to chapter 7. But for us to get going with the basics here, we got to recall that what a function is. Okay, so function, so we have every element in X in the domain corresponds to one and only one Y value. Okay, so if you remember, when you first started to learn how to do this, you did like the vertical line test. And if it crossed more than two places, it wasn't a function. If it only crossed to one place, it was a function. So, I mean, essentially, one X can only have one Y. All right? Well, one X cannot have two different Y's, or it's not a function. So, if a function is defined so that each range element is used only once, that's really what that means. Okay? One X can only have two Y. So X, if X is 2, Y can't be -2 and +2 at the same time, or -3 and +3 at the same time. We just can't have that. Okay, so we want them to be 1 to 1. For every one X, there's only one Y output. Okay, so if a function is 1 to 1, it has an inverse function. So I want you to be careful here. So what this means, when we see this f to the -1, okay, you need to be thinking inverse function. So for yx, okay, and all of xy belongs to f. So we can swap the values around, essentially is what we're talking about. But what you really need to make sure is that you understand this piece. F inverse does not mean 1 over f of x. It is not the reciprocal identity that we've been doing. Okay, it's not x to the -1 and rewriting it as 1 over that. Okay, the inverse function is slightly different. All right, and we got to pay attention to it, how we apply it. Okay, so if we think back to when we've done inverse functions, right? You start with the vertical line test to define if it's a function. Okay, each value of x, one value of y, we determine that. That's what we called a 1 to 1. So remember, when we do inverse functions, the domain of one function is the range of another function, and vice versa. So if we have two functions, all right, so I say we have a function f of x and its inverse we'll call g of x. So the domain of f of x would equal the range of g of x, and vice versa. The range of f of x would equal the domain of g of x. That's really what we're meaning. And it'll make a lot more sense a little later on in the section when we actually graph the inverse functions for sine, cosine, cotangent, secant, and cosecant. You'll kind of see what it means when we're swapping the domain and range of the functions. Okay, but how do we know that it looks like that? It's literally just a reflection across the line y equals x. So whenever we graph something, if we draw a dashed line that represents the line y equals x, and we reflect over that, we get the inverse function. So a lot of this should just be review from like when you talked about this in your comic section and just your introduction to functions and function notation and things like that you've done in algebra. Alright, so if you remember how to find an inverse function. Alright, so we're going to find f inverse of x from f of x. Okay, very first important step, something you should have already learned, was we swap x and y. Alright, but when we do this, we write it in function notation here. So function notation is where we're writing everything in terms of f of x instead of saying y equals something x, right? We're going to say f of x equals something x. Alright, we're really just changing out x and y. So, but what we really want to do though is we are swapping our x and y value and resolving for y. That's essentially all that we're doing. So if we have like y equals 3x, we would rewrite that as x equals 3y and resolve for y. So we're switching x and y, and then we're resolving that after we switched for y. If you can get that down, you're going to understand how to find the inverse function. Okay, so that's really just the steps for doing it. And then solve for y, and then at the end we replace the y again and function notation, so f inverse of x. So don't say f to the negative 1, make sure we're getting in a good habit of saying f inverse, or the inverse function. Okay, so talked about it a few minutes ago. What we're really doing is just swapping, okay, the x and y values. So if you take a look at the graph on the left hand side, okay, we have, maybe the original function, which is the graph of the line there going down that has points BA and AB. Alright, the line y equals x, that's what we're reflecting across to get the inverse function. So what are we really doing? We're swapping the a value and the b value. So in one function it's AB, and the other function it's BA. So that gives us the inverse function. And you guys did this in conic sections as well in your algebra. So if we look at the graph on the right, the original function here is x cubed minus 1. It's really y equals x cubed minus 1, right? Then we swap the x and the y, so it becomes x equals y cubed plus 1, and we resolve that for y, okay? So that's what we're going to get is y equals the cubed root of x plus 1, and then we replace the y with f inverse of x. That's really, the simplistic version of how we find the inverse function. Now, the nomenclature right on your calculator, we have like sine to the negative 1, cosine to the negative 1. Those are buttons on our calculator. Okay, but those are really inverse buttons. That's why you don't get the reciprocal identity. Remember, we have a hard time putting in, secant, cosecant, cotangent. And that button, or those buttons, don't exist on our calculator. But we do see like sine inverse. That is, remember, not, cosecant. It's finding the angle based on the ratio. So another way we call sine inverse is called arc sine. And you might see it in your calculus book listed as arc sine instead of sine inverse. It really means the same thing, okay, as the inverse function. So just a different nomenclature of how we write it. Okay, so let's look at this. We want to find y in each equation. So we're going to run through a few examples here. First one is y equals arc sine of 1/2. I could also write that, as y equals sine inverse of 1/2. That should give me what angle is associated with a sine ratio of 1/2. That's essentially all I'm doing. And so I want you to think of sine of what angle gives me 1/2. That's really what we're looking for here, and that's what it's solving for. Sine of what angle gives me 1/2. So I can rewrite this as sine of y equals 1/2. Okay, so that's really essentially what we're looking at. Okay, so we have to reside between negative pi over 2 and pi over 2 when we take a look at this function. Okay, so the best way for us to look at this approach, is doing a little rewriting. The first piece is understanding, where does the negative pi over 2 and the pi over 2 come from in this picture? Okay, when we swap x and y and resolve for x, okay, it'll make sense once we take a look at the graph here, okay? But what happens is we kind of take that sine value and we rotate it. So now, before our sine wave went from left to right, okay, now it's going to go from bottom to top, essentially. Okay, we're going to come up with how we get that negative pi over 2 and that positive pi over 2. Okay, but those are our new domains. Well, because of normally, where does pi, or where does sine reside, where we get 1/2. Okay, we should know, okay, based on our triangles, how to get these values. So pi over 6, is the same thing as 30 degrees. Alright, remember the side opposite of 30 is 1, and it's a 1 square root of 3 2 triangle. So that's how we can write this and understand. So when I see y equals arc sine of 1/2, what I'm really doing is I'm working backwards. What angle, okay, using a sine ratio, so sine of what angle yields 1/2? And this is where I really need to know my 30, 60, 90 triangle and my 45, 45, 90 triangle. All right, so I can rewrite this and know, all right, that sine of pi over 6, which is sine of 30, is equal to 1/2. So the angle that I'm looking for is 1/2, or not 1/2, I'm sorry, the angle I'm looking for is 30 degrees, or pi over 6, if we're dealing with radians. So if we graph sine inverse in your calculator, this is what it's going to look like. All right, so we have some different restrictions that we have going on. Okay, so when we get, we have sine of negative pi over 2 and sine of pi over 2. And that's what? Between 1 and negative 1. You guys probably aren't following with what I'm talking about right now. So let me step back a step. When we graph regular y equals sine of x, okay, that's an oscillating function from left to right, starting at 0, right, goes up to an amplitude, all right, and it goes through our circular function and repeats itself every 2 pi. All right, so what does that oscillate between? It oscillates between negative 1 and 1. Not looking at this graph's different. This is the inverse function, but the regular sine graph oscillates between negative 1 and 1. If you don't know what I'm talking about, plug it into your calculator, y equals sine of x, hit zoom 7. All right, and take a look at it. You'll see it's a sine wave. The maximum value is 1, the minimum value is negative 1. When we do the inverse function, what are we doing? We're taking that wavelength and we're going up and down the y-axis. Well, it still has to oscillate between negative 1 and 1. So how do we know that? Well, sine of negative pi over 2, all right, so that's sine of negative 90, is equal to negative 1. Sine of pi over 2, okay, is the same as sine of 90, which is equal to 1. So we can look at the range of y as y goes between negative pi over 2 and pi over 2. Okay, this function oscillates vertically now, because that's where the negative 1 and the 1 comes from on the x-axis. So hopefully that kind of helps explain it. But the answer to this of y equals arc sine of 1/2, okay, is going to be pi over 6. We're asking ourselves, what angle or what theta associated with sine gives me a ratio of 1/2. Okay, so let's do this one now. We want to do sine inverse of negative 1. So what is that saying? Sine of y equals negative 1. What angle could y be that when I take the sine of y, I get a negative 1? Well, where does that happen? That happens on a quadrantal. So that happens at 3 pi over 2. Okay, so I can write that out. Now, what's this domain? That's still the domain on y. I explained that with the last graph. So what do we do though? We rewrite this. Okay, so if we look, we went from y equals sine inverse of negative 1. We rewrite that as sine of y equals negative 1. So we're rewriting the inverse function. So then we have to ask ourselves, what value of y that I can take sine of y equals negative 1? Okay, we should get what? 3 pi over 2, or we can get what? Since our restrictions have to be between negative pi over 2 and pi over 2, we have to say that if we plug in sine of negative pi over 2, we get negative 1. Remember, this happens because if we have sine of negative theta, this is a trig identity from chapter 5, if we have sine of negative theta, that produces negative sine of theta. Okay, so what we can do is say we have negative sine of pi over 2 then, and we know sine of pi over 2 is 1, and we have a negative times 1, which gives us negative 1. Okay, so what angle could theta be? So I take sine of that angle and get the ratio of negative 1. Okay, if we were looking on the graph, alright, this is just giving us another view of it. Alright, this one is here to trick you. Alright, it says y equals sine inverse of negative 2. So that would mean sine of y equals negative 2. Is that possible? You should say no, because why? What